My name is Vaishnavi Martaya and my metric number is S23B0136. Linear regression is one of the most commonly used technique in both data analysis and machine learning. It models the relationship between independent and dependent variables. If there are only one input variable, it's called simple linear regression. If there are multiple, it's called multiple linear regression. The goal is to fit a straight line through the data using at least square methods so we can predict outcome accurately. Predicting the dependent variable is key to making better decisions. For example, business might predict future sales based on ad spending or hospitals may predict recovery time based on patient detail. This helps with planning resources, spotting trends early, identifying which factor matter most, and ultimately supporting decision make backup data. Linear regression is a method used to model the relationship between a dependent variable and one or more independent variables. There are two types. For simple linear regression, we use one input variable. Here, y is the value we want to predict, x is the input, b0 in the intercept, b1 is in the slope, and e is the error term. For multiple linear regression, we use more than one input. The equation allows us to predict y using multiple factors like x1, x2, and so on. Now, let's talk about the variable involved in regression. The dependent variable or y is what we are trying to predict. It's also called the target output or response. For example, exam scores can be predicted from study hours. The independent variable or xs are the predictors we use to estimate y. They are also called input of features. For instance, study hours, sleep time, and attendance can be used to predict exam scores. Similarly, our house size and location are used to predict house prices. In short, y depends on the value of x and linear regression helps us find how strong that relationship is. Linear regression is widely applied in real-world situations due to its simplicity and accuracy in predicting outcomes. Let's look at some common areas where it's used. In medical studies, it helps predict outcomes like hospital stay duration or disease progression using factors like age or BMI. For example, a study by Meek and colleagues used regression to predict how long patients would remain admitted. In the finance and economic sector, regression is useful for forecasting stock prices, credit ratings, and market trends. Researchers found even simple regression models could make accurate financial prediction. In education, it used to predict student performance based on variables like attendance and previous grade. The UCI student dataset shows that parental education levels and presence in class strongly affect outcomes. Lastly, in real estate, regression helps estimate house price by analyzing features like square footage and location. The Harvard Housing Dataset is often used for such models. This example shows how flexible and powerful linear regression can be across different industries.
Process of prediction. The first step in prediction process is to determine the dependent variable and independent variables. In this case, the dependent variable is the final exam grade, G3, while the independent variables consist of study time, failures, absences, and the first exam grade, G1. Then, regression model is set. The predicted values for dependent variable G3 are calculated. Based on the data from the calculation, a table for the dataset is generated and the graph is plotted. Next is the assumptions that needed to be taken into consideration for reliable predictions. Firstly is the linearity. This means that we need to perform scatter plot analysis or residual fitted plot to find out that a linear trend happens. Secondly is the independence of errors. This means that the mistakes of one prediction shouldn't have impact on another. Then, the Durbin-Watson statistics or residual over time plot should be performed. The third would be homoscedasticity. We should check on them by using residual versus fitted plot in order to get an evenly spread residuals. Otherwise, weighted least squares will be used to transform the dependent variables and correct them for unequal variances. Finally, is the normality of residuals. This means that the residuals of a linear regression model should be in a normal distribution. Histogram of residuals, QQ plot, and Shapiro-Wilk test should be performed for this assumption.
Model evaluation and accuracy. R square equal to 1 minus SS residual over SS total. R square coefficient of determination. SS residual equal to residual sum of squares. SS total equal to total sum of squares. R square equal to 1 is perfect prediction. R square equal to 0 does not explain any variability. R square higher means better performance. MSE, mean square error. Lower MSE indicates more accurate predictions. RMSE, root mean square error. RMSE helps understand how far off predictions are. Like MSE, lower RMSE equal to better accuracy. Practical example or case study. Case study, predicting final exam grades. Objective, predict final grades G3 using student data. The independent variable is G1, first term grade, study time 1 to 4 scale, absence, failures. Regression equation, G3 equal to 2.5 plus 0.6 is G1 plus 0.8 study time minus 0.3 absence minus 1.2 failure. Example, G1 equal to 15, study time equal to 3, absence equal to 2, failures equal to 0. So the predicted G3 is 13.3. Challenges in prediction. First of all, outliers. Extreme data points can distort the regression line, affect slope and intercept heavily. Secondly, multi-collinearity. High correlation between independent variables make it hard to assess the individual effect of predictors. Use variance inflation factor, VIF or lasso regression. Violation of model assumptions. Assumptions, linearity, independence. Homozydicity, normality. Violation effect prediction reliability and statistical inference. Fixes data transformation, log, square root, or use the other regression models. 8.0 Conclusion. Project use linear regression to forecast student exam score G3 using variable like study time, failure, absence, and G1. Developed model showed perfect R-square score of 1000 with minimal error, indicating possible overfitting due to limited dataset. Emphasize the need to validate assumptions, linearity, independence, consistency, and normality of residuals. Graphical tools, for example, residual plots, histograms, and metrics help assess model quality. Future research should use larger, more diverse datasets to avoid overfitting and improve model generalization. Highlight important of data